We're familiar with how to deal with rate data that's present in a table, but here we're going to look at also how that can be incorporated in different graphs. So let's begin by studying this reaction. A plus B plus C equals some product. Again, if I want to find the exponent for A, I just use the trials that have A changing. In this case, 1 and 2. I can see that I've doubled A, but the rate has remained the same. Hence, there's no effect on the rate by changing the concentration, and we would say that it's zero order with respect to A. Let's start by taking a look at what that would mean on a rate versus concentration graph. I start with some initial concentration indicated on the x-axis, and I'm increasing it to another concentration. The rate, though, doesn't change, so I would have two data points that will lie horizontal to each other. And that means the rate graph would have the following profile. What would a concentration versus time graph look like? Keep in mind that the slope is equal to the rate of the reaction, and in this case, the rate is unchanging. So as a result, if I start at some high concentration and move to a lower concentration through the course of time, I'll have two data points. These two data points must share the same slope because they are the same rate. That generates the following profile then for a concentration versus time graph for a zero order reactant. Let's move on now and take a look at B. To study the effect of B, I want only B changing. That would be trials 1 and 3. Here I've doubled B, and I've also doubled the rate at the same time. That's a proportional effect, so we would say it's first order with respect to B. On a rate versus concentration graph then, I'm moving from a low concentration to a higher one, twice the size. The rate would increase proportionally. That would generate this type of curve, sort of like y equals x, proportional response. What would the concentration versus time graph look like? Remember again that the slope is equal to the rate, and in this case, the slope is proportional to the concentration. So we begin at a higher concentration, and then the reactant is used up. So I would have 2 points. The slope at the higher concentration, if it's twice as much as the lower, would have to be twice as steep. So that would be the slope at the beginning, and this would be a slope later on, half the slope, a proportional response. That would generate this following curve. Finally, to find the exponent for C, I want only C changing, and that would be trials 3 and 4. Here, I've doubled the amount of C, but I have a 4-fold increase, a squared effect. So we would say it's second order with respect to B. A graph of rate versus concentration then would do the following. If I double the concentration, the rate must go up 4 times. This gives the following profile, sort of like a y equals x squared curve. What does this look like on a concentration versus time graph? Again, remember that the rate is equal to the slope. So at the higher concentration in this case, which is twice the lower, it should be 4 times faster. So again, going from a high to a low concentration as the reaction proceeds, my upper point must have 4 times the slope. So it would be fairly steep and then leveling out as we move down to a lower slope. This generates a profile that's also curved, much like our other graph, but it's much more steep. So that's a quick summary of interpreting rate graphs. Thanks for watching.